everybody, welcome to part 6 of the 7-step processor series. At the end of part 5, all the modules that make up the CPU had been described and verified, and then connected into a single CPU module which was dubbed CPU-B. The last thing that was talked about was verifying the CPU design by loading it with instructions and letting the CPU execute those instructions. This slide shows the test plan developed for verifying the functionality of the CPU. First, we need to develop a program using a text editor for the CPU using its assembly language and save it with the .asm file extension. Next, we'll use the assembler to convert the .asm file into a .bin file of binary machine code instructions that are the sequence of CPU instructions for the assembly program. Now we need a way to put those instructions into the CPU's memory so that it can process those instructions. So the next step is to build a Verilog ROM containing the instructions in the binary file. You can do this manually, or this can be accomplished using a special Python program designed for this purpose. The bin2rom.py program reads in a .bin file as an input and outputs a Verilog ROM with the .v file extension. The ROM is also generated with a reg that holds the number of instructions in the ROM. This value will be used by the state machine and the CPU init circuit to keep track of the instructions being transferred. After the ROM is created, it is included in a Verilog module designed for initializing the CPU by transferring the instructions in the ROM to the CPU's RAM. Remember this table? These are the exact assembly language mnemonics that are used in writing an assembly program for the CPU. The assembler will recognize the language and convert it to instruction code. For a quick reference to assembly code in this slide, or the assembly code in the next slide, these are essentially the three categories of words that you will see in an assembly program. An assembly program consists of operands and opcodes, which are code producing commands, directives that are commands directly to the assembler for containing instructions on how to assemble the program, and then there are labels which mark locations in memory. This is the initial test program written to test the CPU in the top section. It is a simple program that adds the numbers 1 through 5 and outputs the result. After outputting the result, the program gets held up in a forever loop until reset or power off. This provides control over the CPU operation once the program is done and prevents the CPU from performing undesirable executions. Now, if you look at the assembly program, we can see opcodes and operands, data and its operands, the data opcode, we have add, the JZ is a jump if, we're going to jump if the Z flag is set, there's a jump, and then we have out and another jump. The directives down here are the .byte 0, and speaking of this .byte 0, for this particular assembler, for the assembler for this program, there's a bug in it, but instead of fixing the bug, this is kind of like a bug fix. While the person who created the assembler either fixes it or not, this putting the .byte at 0 at the end of the program marks the end of the program, and it forces the assembler to work correctly. We also have labels here. You can see the labels, top label, loop top, loop exit forever. They end with a semicolon, and that marks the location to jump back to for instructions, or to jump to when you jump out of a loop. Now, the following are the steps for using the assembler on Windows. Linux instructions are included in the assembler folder that will be put in the GitHub space. And the assembler folder is this on the left, which it'll be cleaned up. Some of these files will be taken out, like the test program and stuff. But the main stuff you need to use the assembler will be there. And so the first thing we got to do for Windows is open two separate folders. One containing the ASM program, which I have here on the right, and the folder that contains the assembler application, which you can see at the top on the left. The next thing we need to do is drag and drop the assembly program onto the assembler application in the other folder. And then what happens is the .bin file is generated within a second or two in the same folder where you had your ASM file. And once the .bin file is created, this is how we can check it in Windows to verify its contents. I'm not sure how to do it in Linux, but I'm sure there is a way if you could look it up. But we can use the format-hex command in Windows, and we can read the memory table that is the binary instruction. So on the top right here we have the memory addresses, and then we have the instructions. And in a minute I'll walk through this program and verify all the instructions. There are 16 total instructions. Here's the .byte 0 directive at the end, which marks the end of the program. Now let me walk through the program. So the first two instructions are 20 and 00. If you look, our first instruction in the assembly program was a data operation. We want to load the value of 0 into R0. And if you look over here, I have the assembly program language on the left. You'll see data is 0010, which for the first nibble is hex 2. And then there's 00, so 2 bits that don't matter. And then RB, whatever the register you want to load. So this instruction 20 is a data instruction to load data into a register 0. And the data that gets loaded is the data in the next byte, which is 0. The next instruction does the same thing, except for we're loading into R1. So there's a 1 here, and we're loading the value of 5 into R1. The next one is loading the value of hex FF into register 2. So these first 6 instructions line up with these 3 data instructions. Now the next instruction, the A4, is an add instruction. If you look at the instruction codes, 1000 is 8 for the first hex instruction, and then 4. So 4 means we're taking R1 and R2. No, I correct myself. R2 and R0, R1 and R0, which is what we have over here. I should just look over here. But 4 is R1 and R0. And then the next one is adding R2 and R1, which is hex 8 and 9. And then now the jump if. If the previous add instruction, which is essentially decrementing our loop variable, then if it reaches 0, we're going to jump to the loop exit. But this is the check that happens. So 5-1, if you look over here, 5 is the jump CAEZ. So you put the letter of the flag that you want to check for. So we're checking for JZ, and that's pretty much it. It's just 5 and then 1, right? Because the 1 designates the Z flag. And so we're setting up the jump if there's a 0, and we're going to jump to 0C, which is the address, the memory location over here, 0C. So we're going to jump over if it's 0. But in the first 5 iterations, it won't be 0. It'll count down from 5, 4, 3, 2, 1 using this add operation. So we're not going to jump until we get to 0. But then what we're going to do is we're going to skip to the next instruction, which is 40, which is an actual jump instruction. So we're going to jump to the address in the next byte. So we're going to jump back to address 06 and then perform, which is essentially going back to the loop top, and perform this 8-4, which is add R1 and R0. Then we're going to add R2 and R1, which is this 8-9, and then we're going to check for the Z flag again. Once again, if we don't have the Z flag, we're going to simply jump back to 06. Now, if we do have the Z flag, we're going to jump to 0C. So we're going to jump over the jump instruction, because now we're jumping out of the loop and we're going to 0C, which contains the instruction. It's an output instruction. If you look over here, for output, we have 0, 1, 1, 1, which is 7, and then an out from RB. So in this case, RB will be out R0, and the 1 for the 8 will be an output. If this were all zeros, it would be input, but since it's an 8, it's an output. We're outputting from R0, and then we go into the forever loop where we just hold the processor, and that's a simple jump instruction. We're going to jump to 0D, which is the location that holds that jump instruction.
So the CPU will just kind of get caught up in a forever loop right here. And here you see the 00 from the .byte 0 that marks the end of the program. So after verifying, it seems that all of the binary instructions are correct. Now you don't need Python if you're going to manually create the ROM, but if you are going to use the Python program, here is where you can download Python. And the latest version is 3.11. I do recommend using Python 3 that is. So here's the next step we need to do. Now we need to generate the Verilog ROM containing the instructions that will be transferred to the CPU RAM by the initialization circuit using the bin2rom.py program, which this is the entire program here. It's essentially a function. We set up some variables down here, call the function, passing in those arguments, and we have a Verilog ROM. So in order to run it, let's see, to use the program, sorry, 1 second please. Okay, what you need to do is you'll set the name of your ASM program, your assembly program. Mine was called sum5. So I'm simply putting that without any file extension. And then what you do is you can run the program. So you can either open up your command line and use the Python programs to run it. So py and then the name of the Python program. Or you can just double click on the ROM. You see all the files are in the same folder. Whatever .bin that you're wanting to convert to a ROM needs to be in the same folder as your Python file. And then what you end up with is this on the left here. I have a Verilog ROM that was generated by that program that contains, or from the .bin file. So to verify the contents of the ROM, what we're looking for is the correct number of instructions. Remember that reg variable I talked about that contains the number of instructions that will be used by the CPU init circuit. So that is correct. We have 16 instructions, so the value of NOI, which is number of instructions, is decimal 16, which is true. And now all of the addresses are, the 16 addresses in the ROM contain the correct information that matches up to the hex values of the bin instructions. So that's verified. Okay. Now, once we have that, we need to include the ROM in initialization circuit. And this is a block diagram shows a high-level overview of the CPU test circuit that will be discussed in further detail coming up. But essentially, we're gonna have a clock that's gonna drive the CPU. Now, the CPU within its control unit has the 3 clock signals. It has the stepper clock, clock E, and clock S. Those signals are now going to be outputted to the CPU init to drive the CPU init. That way there's no other clocks, there's no other clock domains to try and synchronize. It's the same clock for initialization and the clock that the CPU will use to execute instructions. But each system, each component will have its own reset. So what we'll do is we'll start off at reset, then we'll let the CPU init transfer the instructions using the clock from the CPU. The state machine and the CPU init circuit will have control signals that come back into the CPU, mainly for setting the memory address register and setting the address in that, and then also setting the instructions from ROM into RAM. Now here's a basic breakdown of the CPU initialization circuit and the function of the state machine. So when we first initialize, we're going to initialize the address to 0 because our instructions in ROM start at 0. We want to start those in RAM at 0. So we're going to set the address to ROM and RAM to the same address of 0. And state 0's initialization, we're going to set the instruction counter within the state machine to the number of instructions that comes from ROM. And then we're also going to set a loading RAM, which is a status signal, to the CPU, which also drives multiplexers, which I'll show you in a second. Then we're going to set the address into the ROM and the RAM. So ROM and RAM are both pointing to the same address. Then we're going to enable the instruction from the ROM and set it into the RAM. Then we'll decrement the instruction counter because now we have one less instruction. And when we get to 0, which means we have transferred all the instructions, we'll go to a state 3, which is a done state. We'll turn off the loading RAM signal, and the state machine will just set in state 3, it's done. Otherwise, if we have more instructions, then we will increment the address. We'll go to the next address and we'll go back to state 2, set the address, transfer the instructions, check the instruction counter. It just keeps continuing like that. Now here's a breakdown of the state machine I just talked about in a state transition diagram. So right here we initialize the instruction counter, set loading RAM, set the address to 0. State 1, we set the address to ROM and RAM. We enable ROM and set that into RAM, transferring the instruction, decrement the instruction counter, increment the address. Now if the instruction counter is greater than 0, we go back to state 1, set the new address, transfer, set address, transfer. We keep going here until we're out of instructions. Then we go to state 3 where we just turn loading RAM off, and then we will allow the CPU to process instructions. So here's a summary of some changes that were made to modules already created. Very simple changes. The stepper, I added a step 0 as a reset state. So now I can hold the CPU in a reset state. The clocks will still run, but none of the steps are activating, and nothing is going to happen in the CPU. Only the clocks are available to be outputted to CPU init. And then as soon as we deassert the reset, the CPU will begin in step 1 instead of being held in step 1. So now it's actually back to a 7-step processor, but instead of a step 7, we have a step 0. And then the ALU, I needed to remove the carry in, and I'll show you this here in a second because it's wrapping around. So when you have a carry out from an overflow on addition, it's being set into the flags register, and that carry out becomes a carry in, which is being driven back into the ALU and being included in the same addition instruction, which is no bueno. So just took the carry in out. And then CPU B just added some new input and outputs and some multiplexers, which I'll talk about here. Here's the new stepper. Like I said, it's back to a 7-step. So change the register inside of it, the step reg, to be 7 bits now because we have 7 steps, but we're still only outputting 6 steps. And that step 0 is a reset step. So we will hold it in this step 0, and then otherwise the logic, is the same. We'll go from step 1, and then when we get to the end, we'll go back to step 6, and only into step 0 when we hit the reset. And like I said, we'll only output 6 of the 7 steps, same as it was before. So just a simple reset state for the stepper. Now the ALU, like I said, if you go to the ALU, there was a plus CIN over here, like the CIN. We still need that for the right and left shift, but I'm taking that out of the add instruction so it doesn't wrap around and be included in the same add operation. And the CPU B, here are the new inputs and outputs. The inputs are all the ones from the CPU init. So it has the loading RAM status signal. There's a set address signal. There's the address, a set RAM signal, and the instruction from ROM inputted. And then the outputs are just simply the stepper clock and clock E and clock S to drive the CPU init. And I'll show you a diagram of the muxes here in a minute, but these are the multiplexers created inside that are selected based on loading RAM. So if we are loading RAM, we're going to use the input signals from CPU initialization to control the MAR and the RAM within the CPU. And when we're not loading RAM, then the normal instructions from the control unit and data bus take over, like it shows here. So when we're loading RAM, that is our selection signal to all of the multiplexers. And so in that case, all of the control signals for the memory address register and the RAM are propagated through the mux when we are loading RAM, And so they'll be controlled by these signals coming from the CPU init, which will be driven by the CPU clock that goes into the CPU init. And now when loading RAM is 0, all the CPU init signals will be cut off in the multiplexer, and what controls the MAR and the RAM are the internal CPU signals from the control unit and the data bus. Okay, here's essentially a timeline to maybe shed some more light on what's going to happen here. So at the start, we will hold the CPU init and the CPU are both held at reset. We'll wait for a little bit of time to pass, then we'll release the CPU init from reset. And then we will transfer the instructions from ROM into RAM. Then once we have completed that, then we will release the CPU from reset, allowing it to execute the instructions that were just put into RAM until it enters the forever loop. Okay, now for the simulation, there are a couple of questions that need answered concerning simulation time. How much simulation time is needed for all the instructions to be transferred from ROM to RAM? That's what this slide answers that question. So starting at the top up here, so we break it down. If I have a clock where 1 nanosecond, I'm switching it, then the entire CPU clock, so that's a sys clock, so the CPU or the stepper clock is 8 nanoseconds long. Now if I change the input clock to 20 nanoseconds, which is what I'm going to use, then we have a period of a stepper clock of 40 nanoseconds, which if you take the reciprocal of that period, you get the frequency, which is actually 25 megahertz, which is the clock used for VGA. Maybe you'll see where I'm going with the CPU stuff. But now the SUM5 has 16 instructions. So if we take the value that I figure out here, so 8 times 20 nanoseconds is 160 nanoseconds if we're going with a 20 nanosecond input clock. So now we have for the CPU init, there's 2 steps essentially to transfer each instruction. So we take 2 steps times 16 instructions plus 1 more step to get to the done state. And it looks like we need 33 clock cycles to transfer all the instructions from ROM to RAM. And so that calculation, the very last calculation at the bottom, 33 times 160 nanoseconds, gives us the minimum simulation time required to transfer the instructions from ROM to RAM. And so now we need to do the same thing for how much simulation time does the CPU need to complete the execution of the program until it gets into the forever loop. And that's what these calculations are for right here. So we end up with, starting out with the same calculations, we know that we have 8 nanoseconds. The ratio is 8 to 1. So now we end up with 160 nanoseconds when we have a input clock of 20 nanoseconds. And so we take that clock cycle, 160 nanoseconds, times 6 steps per CPU instruction cycle, gives us 960 nanoseconds per instruction. And so now we have to figure out how many instruction cycles. Yes, the program has 16 instructions, but some instructions are repeated due to returning back from a loop, right? So after walking through the program, I've figured out that this program will take 24 CPU instruction cycles to complete. So I multiply that by 960 nanoseconds per instruction cycle and have my minimum simulation time to complete this program. And here is the test bench for the CPU. The diagram shows the 2 models included in the test. So it's just the CPU test is essentially a wrapper that contains the CPU init and the CPU. You can see the 2 modules here instantiated. There's just a bunch of signals to connect between them. The registers in this test bench are simply what we're driving. What we're stimulating is just the system clock, the CPU reset, and the CPU init reset. And you can see the simulation down here based on the times we just calculated in the previous couple of slides. I decided to wait 60 nanoseconds, just 40 nanoseconds shy of taking the init off of reset. Then I'm letting it run that minimum 5280, but I went to 54 until letting the CPU start running its instructions, and then I give enough time. The minimum is 23040 nanoseconds. I'm just running it for 25,000, and then we'll finish. And then this diagram shows all the modules that need to be included for the test. So this is kind of like the hierarchy. And then this here on the right is the CPU test list for Icarus Verilog. I'm going to show you the commands here in a minute. You can use this test list instead of including them all on the command line. And with that, right here are the commands, and now we're ready to run the simulation. You can see how you can use Icarus Verilog. So you start out with Icarus Verilog-O, type in this arbitrary name that you're going to use with VVP. I just called it CPU. And if you use the -C switch and then include that CPU test list that was in the previous file or slide right here, then it includes all of the modules onto this command. Then we can run the VVP CPU and then run GTK Wave to output the simulator. Let me take you to the simulation. Alright, here we are in GTK Wave after you run those commands in the simulation. Now what I'll do is I'll do this in steps because there's a whole lot of signals and I'm not going to cover them all. But I just want you to see that there's no issues, there's no red going on. So I'm going to take all the CPU init signals and put them over into the window over here and then bring that into view. So you can see this first part here where all the signals are crunched up. That's the CPU init part, and I'll blow it up a little bit and bring it over here. Whoops, bring it over here. And you can see here's the reset signal. Blow it up just a little bit more. But and you can see the instructions that are being transferred. You can verify with your .bin. You got 2000, 2105. We're loading data of FF. Here's that add 84, that add 89, that jump Z. We're going to go to 0Z. If not, we'll jump back to 06. Here's the output. And then here's the forever loop of 40 and 0D, and then that .byte 0 to mark the end of the program. Now let me bring in the CPU signals. I'm just going to bring them all in, but we're only going to focus on a couple. I just want to show you a couple of the signals. Now let me bring this back into view. Look at that, it's all green, there's no red, it's beautiful. Right here is what we want to look at, the CPU interface, and we'll focus in right here. How do we know that the Sum5 program worked? Well, let's just look at the output. If you add the values of 1 through 5, you should get the value of 15, which is 0F, which is correct. So if I can change this format to decimal, and you can see that the output is indeed 15. And you can go through all these signals yourself. I'm going to put all this stuff on GitHub. But now I'm going to show you how you can develop your own program to use with the CPU. So I'm going to start from scratch with a new program and get all the way to the simulation on that. Okay, so I wanted to build another program for the CPU and demonstrate how to use different programs with the CPU. So I came up with this. I wanted to see if the CPU can output the Fibonacci sequence. It turns out that it can, up to a certain value, of course, because it's only 8 bits. So I started developing this program to track the operations and data for a possible solution, and then outline the questions for simulation that needs to be answered. So I developed this program for the CPU based on the previous diagram, ran it through the assembler, got the instructions in the bin file. This program needs to use all 4 registers. 2 registers are used to accumulate the sums. 1 register is used as a loop variable that is decremented after each result output, and 1 register is filled with all 1s for adding to the loop variable, which actually decrements the value by 1. Same from the previous program. After each add operation involving the Fibonacci numbers, and by swapping the order of the registers in the add operations, the state of the registers is that one holds the next number of the sequence and one holds the previous number. And then when you swap and add again, you get the same thing. You keep getting the current result, or the current number and the previous number, and then when you add those two, you end up with the current and the previous. You continue swapping the registers. Now to use this program that just created, we've got to go through the same steps. Pretty simple though. Just drag the ASM file onto the assembler, create your .bin, verify your .bin on your command line. Here's all the instructions for the Fibonacci. And now to use it with the, now we have our .bin, there's some changes to, there's 4 files that need to be changed in order to use a program with the CPU and the simulation. So after getting the .bin file, right after writing the assembly, using the assembler, now that we have the .bin file, we need to edit the Python file. Down here at the bottom where it used to say sum5, we change that to Fibonacci. Then we run this program and we'll end up with a Fibonacci ROM. Now that we have, and once we have the Fibonacci ROM, we need to go into CPU init and change this. This used to be called sum5_ROM. It's now Fibonacci ROM. So that's the only thing you need to change in this file. Then we need to go to the CPU test list where this used to say sum5, it now says Fibonacci for the ROM. The only change that needs to be made here. And then now we need to determine the simulation times for initialization and CPU execution, which using the same formulas it did before, using that 160 nanoseconds and that 960 nanoseconds per CPU instruction cycle based on 20 nanoseconds input clock. These are the minimums I got. Then we need to take that and change that in the CPU test file, the CPU_test.v. Just change those 2 simulation times for the new program and leave the same initial reset at 600. And then once we have that, we've made those 4 changes in the files after creating the ROM. We run the same commands as before and view the simulation. And here's the simulation again. Open these up. We'll check out the CPU init first. Make sure everything runs smooth there. Everything's green, no red. Everything looks good. Expand it out a little bit. Then we can check the instructions that are being transferred over. Those are all the instructions there. Now let's check out CPU. We're just really concerned with the output, right? So let's go and look at, if we can find it here amongst all these signals. Let me find the CPU interface line, which should be yellow. Here it is, CPU interface. And now we'll scroll out to where the CPU starts outputting. Here we go. Here's our first value. Let me change this to decimal. So here's where we start. Let me crunch this a little bit. Okay, here's where we start outputting. We're outputting the Fibonacci numbers 1. Here's 2, 3. Next one should be 5, right? Which it is 5. Then 8, 13, 21, 34, 55, 89, 144, and then our final value of 233, which will fit in 8 bits. The next number won't fit in 8 bits. And now the CPU just goes into its forever loop, right? Well, you can see just based on all the outputs, the program seems to be working correctly. Okay, to bring this video to a close, let's recap how you use the CPU in simulation. First, you write an assembly program for it. Use the assembler to generate the binary instructions. Then generate the Verilog ROM from those binary instructions. Then edit all the test files to reflect the new ROM with the new program. Calculate and edit the test bench simulation times. Then run the simulation. All of this stuff that I just went through, it'll all be available on the GitHub space so that you can go and mess around with this processor and create programs for it and simulate it yourself. And so the next part of this, I will be attempting to implement this CPU on an FPGA and running a couple of different programs. Hope to see you then. Thanks for watching this one. Have a great one.